Hey folks, my name is Cole and this is the 13th video in the UP1 final exam study guide. And today we're talking about linear momentum. So linear momentum is a little bit akin to like kinetic energy. It's an attribute that something has because it's moving, specifically because it's moving in a straight line, a linear, momentum. But it's a little bit different. And it's basically a measure of like how much of an impact something would have if it were to collide with something else. So linear momentum we denote with a p, and it is a vector. It's very important. This is linear momentum, and its units are Newton seconds. And the equation for linear momentum depends on two things. It depends on the mass and the velocity of the object. And it's actually a very simple equation. It's that linear momentum is equal to mv, like that. And there's a few things that we can glean from this equation. The first one is that the heavier that an object is, the more linear momentum it's going to have, which makes sense because momentum is a measure of the impact of a collision. So the heavier something is, the more of an impact, the more force it's going to exert on something if it were to collide with it. And then also it's proportional to velocity, which makes sense, again, because the faster something's going, the more of an impact it has, right? A bullet, for example, is not a very heavy object, and if I threw a bullet just out of my hand at someone, it might hurt a little bit, but it's not actually going to harm that person. Whereas if I shoot a bullet at, 80 meters per second from a gun, now the bullet becomes a lot more dangerous because it has a much higher momentum because of that v term. The other thing to note about this equation is that it is a vector equation, and we can see that just like the F equals ma equation, the only two vectors are p for momentum and v for velocity. They're on opposite sides of the equation, and that means that the direction of the momentum is equal to the direction of the velocity. And that's like kind of it for linear momentum. It's a very simple equation. What we can do now is we can do a couple examples. So just conceptually, if I have a mass here that is 4 kilograms and it's going to the right at 2 meters per second, we would say that this thing's linear momentum p is equal to 4 kilograms times 2 meters per second, that direction, which is 8 kilogram meters per second to the right. And a kilogram meter per second, well, that's a Newton second, because a Newton is a kilogram meter per second squared. Multiply that by seconds, you get kilogram meters per second. So this is 8 Newton second to the right. Another thing to note about momentum is that it is additive within a system. So we can define the momentum of an entire system of discrete or uniform bodies. And that's going to be really helpful when we start getting into like conservation of momentum, because we're going to have to describe the momentum of multiple objects at once combined in order to conserve momentum within a system that experiences a collision. So we can say, for example, that if we have one mass going at 3 meters per second at a 45-degree angle below the horizontal, and another mass going directly to the left at, let's say, 2 meters per second, and let's say this one is 1 kilogram and this one's 2 kilograms. Okay, we can define the momentum of this entire system, right? This entire system of the two balls moving has some momentum. Let's calculate it. Things to remember: first of all, momentum is additive. Second of all, momentum is a vector. We cannot just add 3 times 1 plus 2 times 2 and say that the total momentum is 7, because it's 7 what? 7 Newton seconds in what direction, right? We have to do vector addition. So what I'm going to do is I'm going to split momentum, the vector p, into its x and y components. And I'm going to say that px is equal to, if I call this m1 and this m2, it's going to be px1 plus px2. All vectors. Okay, So what's px1? Well, it's the horizontal component of this momentum vector, that one right there. So that's going to be 3 meters per second times 1 kilogram times the cosine of 45 degrees, which is root 2 over 2. We're going to add to that the x component of this vector. That's 2 kilograms times 2 meters per second, but let's be careful here because I didn't do it like flat out. I didn't tell you I was doing it, but in calling this velocity vector positive 1 times root 2 over 2, or positive 3, I should say, meters per second times root 2 over 2, I defined it a set of axes. I said that this direction is positive x, and I have to stick with that now, which means that this direction, I'm defining it now as positive y. So let's stick with these axes. This one is now going in the negative direction, so I'm going to multiply this by negative 2 meters per second, and that's my total momentum in the x direction. Now this makes sense because this mass is moving in the opposite direction as this mass. So their momentum shouldn't add to a bigger momentum, right? If they were to hit each other, some of their momentums would cancel out. They wouldn't start going faster in a single direction. They would start going slower. So that's why we have to treat momentum as a vector. And this is equal to, I guess, 3 root 2 over 2 minus 4 Newton seconds in the x direction. And now we can calculate Py. Py is going to be Py1 plus Py2. What's Py1? Well, it's the same as Px1 because we're at a 45-degree angle. So it's going to be this component of the vector, which is 3 times 1 times sine 45, and sine 45 is still root 2 over 2. So this is going to be 3 root 2 over 2 plus Py2. Well, what's Py2? It's 0, right? Because there's no vertical component of this momentum vector. So it's just 3 root 2 over 2. So the total momentum of the system is 3 root 2 over 2 minus 4 I hat plus 3 root 2 over 2 j hat. Now, if we wanted to, we could do what we learned in the first video about vectors, and we could calculate the magnitude of this vector using Pythagorean's theorem and the angle of the vector using inverse trigonometry. I'm going to stop this here, though, because we've already gone over how to do this, and this is what I have for momentum for now. Now, we're going to talk a lot more about momentum when we get to conservation of momentum very, very soon, but in the meantime, our next video is going to be about impulse and changing momentum.